I'm going to finish off the last objective here, objective 3 in rectifiers and battery chargers part B. So we've talked about rectification now. Now I want to kind of dive into a practical application for rectifiers. So battery chargers, at least hopefully we've all seen these or potentially had to use them either for work or home, where we have a charger that we've plugged into 120 volts and we hook it up to our battery to charge it. So the expected output there would be DC to charge our battery. So 120 in, AC in, and output DC for our battery chargers. So again, many chargers are basic rectifiers, while others have automatic adjustments that set charge rates, times, float voltages, on and off, and high and low cycles. So we'll talk about our basic ones here, but they do come in all different styles. Battery chargers are rated in capacity. So the DC voltage output is typically 612 or sometimes 24, depending on the voltage of the batteries they charge. Okay, so that's a battery selection where I'm like, I need to charge a 6-volt battery, so I'm going to put it on 6 volts. Or I need to charge a 12-volt battery, well, I may have a slow charge and a fast charge at 12. Okay, but these selections are for the battery, or a 24-volt battery, that we're going to charge, not the output voltage. Okay, that's going to be different than that. So a small automotive battery charger would have the rating that the table shows below. So again, we could, depending on what type of battery, it could be fast or slow charge. More current, obviously higher charge. The charge trickle charges, so charges at a slow rate, 6 volts, 12 volts, batteries at 2 amps, and fast charges, 12 volt battery at 10 amps. The output voltage and current are determined by the selector switch. Okay, so look at this diagram here, where we show the two main sections. So here's our rectifier section. So we can see we have diodes here in sets. We'll explain this. It's a center tap, as we can see, but there's two center taps. So what they did was actually put these diodes in parallel with each other so that they can share the current. So we know that in parallel we split the current. As long as these diodes are rated exactly the same, they will share the current evenly, and that's exactly what we want to do. So it's still a center tap, it's just we've paralleled this to take advantage of the fact that we can split the current over them. Okay, here's the transformer section. So here's our primary windings and our secondary. Obviously we're through our mutual induction from our transformer. So we have a 120 volt supply, so it depends on the selection here as to how many turns we have on our primary to induce a voltage into the secondary. So we can basically select the output here, and it's going to change the amount of current that's going to go, whether we're high, medium, low, again 12 volt or 6 volt. Obviously there's an indicating light showing that we have 120, so there's across the 120. A timer motor also needs 120. Again, if it's not going to start until you actually turn that dial to start timing, then it'll close those contacts and start charging. On the back end here, we have, looks like a breaker potentially here, a resettable breaker if something, shorts out or anything here on the load side. So this is where the battery would be hooked up. We have a rectifier that's taking the AC, so in from here on our full secondary, getting it to our center tap rectifier, and then having our output. Then we got a light emitting diode here that's going to indicate that we're charging. And then we have an ammeter potentially here that's going to show us the current going to, again, our output or to our load. So the transformer section allows 120 volt input to be stepped down to provide proper voltage levels for battery charging. Has 5 taps, rotary selector switch used to select one of the 5 settings. Again, that's going to change the turns on the primary, which is going to induce a different voltage for us on our secondary based on that. So the 6 volt and 12 volt setting indicate the type of battery charger that is connected to, not the actual voltage applied to the battery. Changing the setting from low to high increases the volts per turn ratio of the primary and increases the voltage output of the secondary to the rectifier. The secondary of the transformer has 2 center tap windings. 2 parallel windings reduce the required secondary winding conductor size, providing increased current capacity at a lower cost. So basically, in this transformer section, what it's saying is if we parallel these two, we can get twice the current because these only have to be rated for half of it. Okay, so just in regards to cost, that's a huge cost, and these conductors too would be half the size they would be if we just had one diode here for the portion of the center tap. Okay, so that's why they're paralleling these. That's why there's two here when our regular center tap showed just one here and one here. We've got them split into parallel just to take advantage of the fact that now we can split the current, have smaller conductors, smaller diodes with smaller ratings, everything. Okay, the rectifier section, again, the arrangement is two parallel single-phase center tap rectifiers. When diodes are connected in parallel, again, each one is accurately tested and closely matched pair because they have to share that current equally. If they're not, one will take more and potentially damage the diode. The double winding diode arrangement increases reliability if one fails too. Okay, so if one failed, it would potentially, it would depend if the full, I would say one set's going to fail, we'd get into a half wave rectification. So the charger would still work, it just wouldn't output as near as, it would basically output half. But to me, if one of these diodes failed, the other one would be forced to carry the current and would probably fail as well too. But yeah, if both of these are out and we only have one, now we're into half wave rectification as well too. So to look at the actual design still in this rectifier, this charger uses two 50 amp rated diodes in parallel rather than one diode in each leg. That allows each leg to carry 100 amps. Okay, so 100 amps because of the parallel connection. However, with a center tap rectifier, each leg carries only half the current. Okay, and that's like what we talked about before for rectification. If a diode's only on for one alternation out of two in a full cycle, it's only having current go through it half of the time. So on average, it's basically rated for half the current. So that's where we get this double multiplying scenario happen. So if the diodes are rated for 50 amps, I can get 100 amps through them basically because they're in parallel, okay, because they're going to split that current in half. But then also because they're only on for half the time, I can double their rating again. Okay, so because it has parallel diodes, that's why I can multiply it by 2, or because it's center tapped, again, I multiply by 2 again. So it actually has the capacity to have 200 amps instead of the 50 that they're rated at. Okay, and again, just because of how they're connected in parallel and the fact that they're only on half the time with our center tap rectifier. Okay, so that's where they're getting the double thing. So if they said, I have a 200 amp load, what size do the diodes need to be? Well, it's literally just the opposite. You would just start at the 200 and work your way back and divide by 2, and then you'd get your rating. Okay. Other components they have: overcurrent circuit breaker, an ammeter, correct polarity indicator, charge time clock. Again, this is usually a timer because you don't want to leave your batteries charging unattended for extended periods of time because it could overcharge and then the battery explodes and smokes out and causes damage, could cause a fire too. Okay, so they're usually on a timer. Settings, so to change the current setting by adjusting the voltage input to the rectifier by changing the taps on the primary of the transformer with the selector switch. So here's our different taps, 6 volts and then 12, low, medium, and high. Okay. Higher voltage to a battery causes higher current flow. So when we were looking at, they did this test was basically with load amps of 0, 50, and 100. Okay, for every selection it did that. So it went from no load, half load, full load for each one. Then it showed the peak volts for all those, and then the current, and then the meter volts. So this is the peak of the secondary, and the meter would read VDC. This is the DC output. Okay. So again, higher voltage causes higher current to flow. The results in the table below are obtained by loading the charger to 0, 50, 400 at its 4 settings. Okay, so again, just to look at some of this stuff here so that we can see that there's what some of these numbers are doing. We have our peak volts, and then we use that percentage, that 637%, and that's going to give us this expected VDC. So we're just timing the peak by that percentage, and we're getting this expected VDC output based on the peak volts. Now they say the voltage change, we'll talk about coming up here, basically because of the volt drop across the PN junction of the diodes. So that's what you're seeing change as we start loading this up. There is the current is increasing, so the IR squared or I squared R losses, I guess, in the windings too would potentially create a volt drop, but they said it's mainly for the PN junction, the volt drop across the diodes. Okay, so this kind of shows that what's happening when it's charging, and the amount of current that's going through there is based on the difference between the charging voltage and the actual battery voltage. So they're using the 12 volt high setting at 50 amp and 12 volt low. So 12 volt high at 50 amp is 18 volt peak, and low is 16 volt peak. So we're just comparing them both at 50 amps, the 12 volt high again at 18 volt peak and 16 volt peak. So the difference between the 12 low and the 12 high is the voltage output level. Again, the difference between these two numbers. Figure 25A shows the output rising to a peak of 18, and 25B shows it to 16. The horizontal 12 volt line represents the voltage across the 12 volt storage battery. The current transfer or charging happens when the charger voltage is higher than the battery voltage. The 18 volt peak setting delivers more current than the 16. So if there's a bigger gap between the actual battery voltage and the charging voltage, it's going to be higher current. And it's going to be charging for longer because it's got this gap here that's very small, so it would be charging off, charging off. Where here we're charging and we're off for longer because it's getting closer to the actual peak voltage. Okay, and would be drawing less current at that time. It's on for less, drawing less current, as opposed to here on longer and charging at a higher current. Again, just the difference between the peak and the actual rated battery charger voltage. So again, the current is greater when the battery voltage is low. Again, low difference between the peak and the battery value itself. And the battery voltage is greater, so the current is less as the battery nears full charge because the difference in voltage is smaller. This is the trickle charge effect. Okay, so I have this peak charge voltage, I have a low battery voltage, so it's on for longer because it's got to charge more and drawing more current at that time as too. So it's off for a very short period of time here when the battery is low. As the battery gets higher, so as it charges up, it's going to be on for less and off for longer. That's that trickle charge part of it. So now it draws less current because it's basically less difference between the peak and the actual battery voltage, and it's not charging for as long either, and will eventually taper off when they are equal. Test results show that an open circuit 12 volt low setting is 18 volts at 11.5 VDC. So low setting 12 volt is here is 18 under no load is our peak, and we get this 11.5. Just showing you that we're just using our percentage. This is again is our VDC output based on that center tap rectification. So when a 50 amp load is connected to the charger, the peak average output values drop from 16 to 10.2 respectively. So compared to the 18 and 11.5, now they're saying we're comparing, look what happens when we go to 50 amps. The peak goes down to 16, and the meter, or our VDC, went down to 10.2. The volt drop is partially due to the drop in the transformer winding, again, but mainly because of the forward voltage drop of the silicone diodes. Okay, so it's kind of, that's what they're explaining why we're seeing these volt drops here. At higher values of current, we're going to have a larger volt drop across that diode. With a 100 amp load connected to the charger, the peak average output values drop for 15 and 9.6. So now we're looking here and here, which shows the full effect of the silicon PN junction and forward volt drops. So again, from going no load to full load, we've dropped 3 volts here and almost 2 volts here. Okay, so just showing that differences when we have current going through there, we do see a volt drop across that diode. Troubleshooting: if the AC input is verified and the output circuit breakers are closed, the remaining components that may fail are the diodes, transformer, and terminations. If one pair of diodes has failed open, the output waveform appears as a half-wave rectifier instead of the 2 pulses of a full wave. If you use meters instead of a scope, the output voltage and charging current are 1/2 the value of the normal circuit, and it would take twice as long to charge. So it'd still work with a failed diode, but it would work only half as good, because we're missing this alternation now, because now we've gone from full wave to half wave. Our percentage went from 637 to 318, and now we are getting half of the expected output to our load, which is our battery, so it would take twice as long to charge. Okay, this is just some things we can check, and some expectations. If we go from full wave to half wave rectification, what's going to happen? And then here's just a little thing is in your in your ILM. This is basically in regards to the first 2 objectives, kind of a Cole's notes of all the rectifiers and their percentages, their outputs, their VRM, the ripple. Okay, it's just kind of a shorthand, tidy version of all the different. So here's single phase half wave, single phase full wave center tap, single phase full wave bridge, half wave 3-phase, and full wave 3-phase. Okay, so this is kind of handy to kind of tally things up for us.